So there was another typo I just wanna to show. So I accidentally had a 0 here, and let's see what the consequences are. So we're just running now network, and of course, if I set this to 0, so that was the typo before, but it's correct in the slides, then that doesn't have any effect. And we can actually check this by looking whether we have layer weight momentum. So if we go to dense, for example, dense 1, then we see it doesn't have this attribute, and also the values are not really impressive. So now let's say momentum. Compile it now and run it again. And then we'll see it has a dramatic impact. And it's pretty close to the record, 93.8. And now if you go to dense 1, then it has the bias momentums, and it has the weight momentums. All right, so now we want to modify the code a bit. So we want to put this into a function, or turn this into a function. So let me just copy and paste this here and remove it here, because we're gonna run this many times now, and it makes more sense to put this in a function and run the function then. So we want to call this function then, yeah, just run my ANN. And as input parameters, we can actually set the learning rate, decay rate, and the momentum. We can already take those values here, because it turns out that they make sense and give a relatively good result. So therefore, we don't need it here anymore. And here we go. And we can also use n. So that's the number of epochs. So it's called epochs. And we can also set this to 10,000, which is our default value. Then, of course, we have to be careful here and say, okay, this is then an epochs. And the next thing is that we have to put this so that we have to add 4 spaces. So we have to shift this to the right. And then we don't have further error messages. Yeah, that's a error message because of that. Okay, and then we also want to save this as a function. Okay, run my ANN. So let me just remove that and remove that, and then we can just see whether it works. So let's make a test run. So we have all the default values. We just leave them as they are, and it runs. Okay. So, and creates the plot. So what we want to do now is to evaluate the quality of the result, not only just with this plot here, but also really with this plot. So we want to create this plot again, but then we also want to add colors to these data points according to the predictions. So we want to do the following. So we color these data points according to the actual classes. So that's what we're going to do with the face color. And we add on top the edge color according from the predictions. So we can actually save this particular plot here. Can just copy and paste this, right? And can actually create more space here. Yeah, like this. And we want to create this plot here. We want to avoid to plot the first plot over the other one, so we can just say plot show, just to make sure. All right, so then we want to create this plot here, and then we want to plot the predictions on top of that. So first of all, we have to run this here again. But now we want to do this with the predictions. So we just look at the predictions here. And want to see where this is 1 or 2, because then we have the indices for the predictions, and we want to call this with P. And then we want to plot or create the same plot, but this time with the predictions. So we just add the P here. And also here, and also here. And now we want to create a plot where the face color is none, and the edge color is then according to the predicted classes. So therefore we have to distinguish between different colors. So this would be the edge color. I think the keyword is actually edge colors. Now let's try it. Yeah, edge colors. And then we also have to set the face colors to 0 or to none. So there's still a problem with that. IDX. Ah, yeah, so that's the P. Sorry, that's another typo. So it's always good to look at the warnings. And of course, the same problem is here as well. Okay. So we just look at the index where the indices where the prediction is 0, 1, and 2. Then we can create the same plot as we see on the right-hand side, but no superimposed by the predictions, and that we really see a difference. We set the face color to 0, to none, so it's transparent, and the edge color to the same color. So ideally now we should not see mixed up colors. And we want to try that. And let's, for example, start with a small number of epochs. So n epoch equals, I don't know, just 300 or so. So the accuracy should be relatively low, and we should see lots of mixed colors. So let me just remove that here and run the code. And then let's expand this a bit so that you can really see it's actually pretty good. So most of the data points are perfectly classified. Some of them right in between those different galaxy arms, so to say, where they're overlapping, they're misidentified. That's what you see here now. So the face color comes from the actual class assignments. So that's the true class. So that's the correct class, and the edge color from the network. And you see the only parts where it's actually not correct is really where they overlap. There are a few exceptions here, of course. But considering that, and that we have only 300 epochs, that's actually pretty good already. And then you see really how it actually outperforms standard approaches like k-means or so would completely fail there. So let's try this now with 10,000 epochs again, so we don't need to set this value. Sorry. Then we will see that it improved a lot. You see actually that creating the plot also takes a considerable amount of time. All right, so we have the result when we after 300 epochs, and the accuracy was something like already like I would say almost 80%, and after 10,000 it's 92.3%. It's pretty close to the absolute record so far, and then you see only a few misidentifications. So it works, and we can also evaluate the progress by creating this plot. And of course, we want to apply this network at some point. So therefore, after everything is done, we want to save the weights because we want to use it for an application then. So therefore, after all the epochs, we just go down under the loop, and now we want to save the weights in the biases because that's the memory of the network. So we just say np save, and we want to save the weights with weights 1, referring to the first layer as NumPy array, and we want to do this with dense weights, and we want to do this with both. And we also want to save the bias. All right, then let's run the code again. All right, so it's done. And again, we have more than 90%, and this time it saved the weights, so the biases and the weights. And now we can use that as a memory for the neural network, and can now write a function that I want to call apply my ANN. So the idea, of course, is that we have new data of unknown classes, and then we run our network. So we just go to our network and copy and paste a few things. So for example, we want to import NumPy and we want to import the network. So we just go up there and just import those things here. And then we want to load those weights. So we want to call them W1 and we use np load. And we want to load those weights that we have saved earlier. And we also want to do this with the biases. All right, and now we only have to go through the forward part. So we will now load these weights and we want to implement them into our layers. So we first of all essentially just copy the forward part. So we first of all of course have to call the activation and the two dense layers. We do not need to call the optimizer and the loss function because we only need it for optimizing the training process or for optimizing the cost function or the loss function. And of course, we don't need to do that now. So the only thing that we have to do now is processing the new data points through our layer and get the output. So we just call our layers here. And then we have to reset the layers at the weights. So we just go to dense 1, weights. And this is then just W1. And we do this with dense 2. And of course, we are going to do this with the biases as well. And then we have implemented the memory from the trained network. And we just go through the forward part. So we have the new data. And then we just go through the forward part. And then we will get an output from the dense layer. Okay, so, and from this we can calculate the probabilities, and from this we can calculate the predictions. So let's call it result. So that's the output from the last layers. These are not the probabilities yet. So we just have to add the probabilities. What is missing then is turning the output from the second dense layer into probabilities. So in principle, we can now actually call our activation function our Boltzmann distribution, but we can also just, to keep it simple, just go here and just copy and paste that. So we just copy and paste this part here. And then the input, of course, so it's the result. And then we have the probabilities and can look for the predictions. That we get here. And we can actually return this as an output of this function. So what the Boltzmann distribution did earlier, that's what we do here explicitly. So it's still the Boltzmann distribution. So we have the exponential values from the result and calculate probabilities, and from this we calculate predictions. We want to have this as an output. All right, so then we're actually ready, and we want to save this, of course, under this particular name. Here we go. And now we want to do this, apply this to a new data set. So we have now our weights, and we want to apply this to a new data set. So we just, in principle, just call this here again. Maybe with a different number, but of course still 3 classes. And then we have our x new here. So if there's our x new here, we feed it in. And of course we have to know these parameters here. And how does it work? So we know that this here is the number of features. So we just go to x new, and determine the shape. And then we have the number of features which you have in x new. In principle, we could also do that with the weights, because remember the weights were number of features times number of neurons. So we could also go and say that we take a look at the first weight, then we determine the shape. And then S1 is still the number of features. And S0 is the number of neurons. And this here is the number of categories. So we kind of, in this sense, have to hard code this. So the number of categories is 3. So let us check whether we can load our weights. Then we go to weight shape, and we get the shape. So we have 2 features. Sorry, then this has to be 0, and this has to be 1, of course. So it's always good to check, right? So we have 2 features and 64 neurons. And of course, we apply our network, we don't need to know that. but you see already the limitations here. So if we have trained it for 3 different categories, then of course the output is for 3 different categories. All right, so now it should work, but maybe we're gonna find another error message and then we're gonna fix that, but that's the idea. So now as an input, we have the new data, we load the weights. From the weights, we can reconstruct the shape for the dense layers. Then we replace the weights from the initialization with the weights from the trained network. So we transfer the weights and we do the same for the biases. And then we go through the forward part till we have the probabilities and the predictions, and we will want to have this as an output. Okay, so we just then go to our test, and this will be our X new. And we feed in X new to our new function, which is called apply. Oops. So let me just rerun it again. Let's apply the autocomplete. Yeah, let's check whether it's been recognized. So apply my ANN, and then we have X new. And of course, from X new, we don't know the actual classes. So we now want to create a plot. And we also want to check the predictions then. So we just go look at the predictions. And create a nice plot. Okay. So of course now we can't compare it to the actual class because that's what we usually don't know, right? So just keep this in mind. So that's what we don't know. We still can actually do that. We will because in our case we know it, so we still want to evaluate how well we can apply our neural network to the new data set. But in practice, we do not know why, right? So we don't know that. So therefore, let us first run the code and test the code now. And of course, we have to run this part first. There's a comma that's missing. Just restate it, you see the typo. So there's a comma missing, and then we just run this code here. Then we have our predictions. And these are our predictions. And then we can create a plot based on this. And hopefully it looks a bit like our galaxy plot. And it doesn't look so bad. And let us cheat in this case. So let us now overplot this with the true class. And again, that's something we don't know, right? We do not know the true class if we apply it to new data. So we just copy and paste that. And then we have y, and we just copy and paste that. And now we can create a new plot. And you see, it was not so bad, right? So only there where they kind of overlap, we have some misidentification. And that's how you actually do that. So you first train your network, then you save the weights and the biases, and then you apply the exact same network. So again, you have the network, you run network and train it, then you save the weights and the biases, and then you apply it to new data where we do not know, of course, the classification, and you just transfer the weights from the trained network, and then go through the forward pass, calculate the predictions, and here they are. And again, remember, what you know is actually this. You don't know this here. That's just for comparison. And let me just go back to the slides to just show you a few results, and we just play a bit with the data. So when we use a sample size of 100 1,000 data points, so we used only 200 each, and then we apply it to 1,000, then we see there's almost no misidentification, because 1,000 is really a lot. That's really 1,000 per class. And then apply to 100 data points. It's kind of what we did now. Then you also see that's almost no misidentification. So the code works. Everything works perfectly. We can apply new data to the trained network, and that's part one. So we are done with part one. So congratulations if you have followed so far. And in the next part, which is part two, we want to use the core that we created now with the optimizer, the dense layer, the softmax layer, and everything, to add it to a convolutional network where we want to categorize different images, cats and dogs. And therefore we have to add a few more things. So that will be the second part. Then thanks a lot for your attention, and I hope it really helped you, and I hope you can really you really learned something from that.